In the vast and intricate world of mathematics, science, and really any field that works with large or small numbers, there may be instances where you have to encounter scientific notation. So, in essence, scientific notation is a type of notation we use when we're dealing with rather large or rather small numbers that becomes like rather troublesome to write out. So for example, like the number 300 billion, right? That would be kind of like a lot to write out. So instead we can use scientific notation, which kind of helps numb down the amount of writing or the amount of zeros that we'd have to write. So let's just get right into it. So scientific notation, at essence, contains a coefficient, which we're going to call a base, which is the number that's attached to the exponent, which the base with scientific notation is always going to be 10. Now, there's an exception. Occasionally, scientific notation can be written as a times this letter e, which it's actually capital usually. So a, e, and then raised to whatever power. And usually the letter e, you only see that in your calculator, because sometimes in calculators you can also input or put in scientific numbers and scientific notation, and there's like an e button that you can use for that. But in this course, we're going to see scientific notation as so. So we're going to have a, which is some sort of number, a decimal, times 10, which is the base, and b, which is the exponent. And the exponent, depending on what number you have, so if you have a negative number, that's indicating that you're dealing with a smaller number. And if you have a positive exponent, that means you're dealing with a rather large number. Alrighty, so let's take a look at how to convert numbers to scientific notation and how to convert scientific notation back to its original form. So you can go ahead and use this diagram, which, so like let's say if we have something in scientific notation, we have a positive exponent, that means we're going to move this decimal that we have here to the right. So in this case, because it's positive 4, we're going to move it positive, or we're going to move it 4 places to the right. And this makes sense, right? Because before I mentioned if you have a positive exponent, that means you're dealing with a rather larger number. So to make 3.2 larger, you're going to need to move this decimal place from here and go to the right to make it larger. Because if you move it to the left, the number is going to get smaller, right? So that's this kind of idea. So now, on the other hand, though, if you were to have something like 3.2, which is the same 3.2 times 10, but with a negative exponent, this time you're going to move it left instead of right. So look at the difference. So we see here this is negative 4, and we have 0.00032, which this is significantly, like it has a significantly smaller value than times 10 to the positive 4, which is 32,000, right? So the exponents play a big role in understanding what a negative exponent means and what a positive exponent means in terms of scientific notation is very important. Alright, so taking a look at example 1, we are asked to express the rational numbers listed below in proper scientific notation. So for the first example, we are given 0.0034. So whenever we are dealing with scientific notation, up here there's a note that I didn't go over per se necessarily, but a is going to be our decimal, right? But specifically a, our decimal needs to be either equal to 1 but less than 10. So it can't be greater than 10, and also can't be less than 1. So what that means is that our decimal place is going to have to go over right 1, 2, 3 places. So we get 3.4. Let me rewrite that. So this decimal in scientific notation is going to be 3.4 times 10. And now, is our exponent going to be positive or negative? I encourage you to pause the video and think through that. And assuming you've given it a go, let's go through this. So the first thing is, because we're dealing with a decimal, our exponent automatically is going to be negative, right? So we know it's going to be negative, and now we just have to simply look at how many decimal places we moved to the right. So we moved right 1, 2, 3 decimal places. So this exponent is going to be to the negative 3 power. Looking at example number 2, we have 4,456. And I encourage you to pause the video and convert this number to scientific notation on your own. And assuming you've given it a go, let's go through this. So because this is a rather large number, right, we automatically know just by looking at it that our exponent's going to be positive, and we want to make this a decimal. Now, some of you might be wondering, I don't see a decimal place here, so how can I convert this to scientific notation? Well, if we simply just add a 0.0 at the end, that can be our decimal place, right? Because when we add a 0.0 to the end of any number, that's not actually changing the value of the number. This is still 4,456, right? So if you see a number that doesn't have a decimal, for example, up here we had 32,000, there's no decimal place here, but we still converted it into scientific notation because we can add a 0.0 at the end and then move that decimal place. So this one's going to be 1, 2, 3 decimal places. 3 decimal places. So we're going to have 4.456 times 10. And because we moved it 3 decimal places and we're dealing with a large number, it's going to be to the positive 3 power. Alrighty. Looking at example 2, I encourage you to pause the video and work through this both examples 3 and 4 on your own. So what you're going to have to do is you're going to have to take the numbers that you're given in scientific notation and convert them back into a rational number, which are these numbers that you see here. Or not these specific numbers, but numbers as so. Alrighty, so assuming you've converted both these numbers in scientific notation back to their rational forms, let's go through it. So for example 3, we have 2.36 times 10 to the negative 3rd power. Because the exponent is negative, I know I'm going to be dealing with a rather small value, right? So to make this number 2.36 smaller than what it's given in this form, I'm going to need to move that decimal place to the left. So what we're going to get, I'm going to need to move it over 3 places. We're going to get 1, 2, 3. And I'm going to need to fill in these gaps. So we're going to need 2 additional zeros and then a decimal place here. So we're going to get 0.00236, and that's it. That's your answer. Looking at example 4, we have a positive exponent, which means our number has to increase in value. So knowing that, I'm going to move my decimal place to the right, and specifically by 5 places. So we're going to go 1, 2, 3, 4, 5. Now let's fill in the gaps. We have 1, 2, 3 missing zeros. So we're going to get 73 and then 3 missing zeros. So this ends up becoming 70. Oh, there's a 5 here. So this becomes 573,000. I just missed that 5 here. Alrighty. So for example 3, now that we understand how to convert scientific notation, we're now going to use our previous knowledge of exponent rules that we looked in the past couple sections and apply it to scientific notation. So for example 5 and 6, we're going to be adding and subtracting scientific notation. So the one thing to note here about it specifically is that to add and subtract numbers in scientific notation, to add or subtract, we need to have the same base and power. So we've seen this before when we've had to combine like terms, right? So recall the base is what's attached to the exponent. So in this case, for scientific notation, our base is always the same because our base is always 10. So that we don't really need to worry about in terms of scientific notation. But in scientific notation, what we do need to pay attention to is the power. So looking at example 5, we have 5.3 times 10 to the 8th power plus 3.1 times 10 to the 9th power. So these are two different powers, which means they're not technically like terms and we can't combine them. But we know how to convert numbers in scientific notation, so we can use that knowledge to make one of these exponents common with each other. So what I'm going to do is I'm going to take this first term here, 5.3 times 10 to the 8th, and I'm going to make that exponent become a 9. And how would I make this exponent go up by a value? All I have to do is simply move that decimal place over left one value. So that gets us 0.53 times 10 to the 8th power plus 3.1 times 10 to the 9th power. And, oops, not to the 8th power, to the 9th power. And now because our exponents are the same and our bases are the same, all I have to do is take 0.53 and add 3.1 to it. And 0.53 plus 3.1 is 3.63. And now all I have to do is carry along that times 10 to the 9th power, and that's your final answer. Looking at example 6, I encourage you to pause the video and work through that on your own. And assuming you have given it a go, let's go through it. So we have 5.6 times 10 to the negative 5th power minus 3.6 times 10 to the negative 4th power. Now, because our exponents aren't the same, I'm going to need to make one of them. I'm going to need to change one of these numbers that we have here. Or not change the numbers, but change the value of the exponent by moving over a decimal place. So I'm going to change this first number here, and I'm going to move that decimal place to the right by one value to make that exponent a negative 4. So we're going to get 0.56 times 10 to the negative 4th power minus 3.6 times 10 to the negative 4th. And now because our exponent's the same, all I have to do is take 0.56 and subtract 3.6 from that. And that ends up becoming negative 3.04. And then we're going to carry along that times 10 to the negative 4. And that's your answer. Looking at example 7, we have 6.8 times 10 to the 12th power divided by 3.2 times 6 to the 6th power. So here, these examples are a little bit easier. All we have to do is use the exponent rules we've seen before. So we're going to divide our numbers. So we have 3.6 divided by 3.2, which that is 2.125. And then here, we're going to carry along that times 10. And our exponent, what we're going to do is use those exponent rules that you've learned. And when you divide, recall, that means you subtract. So in this case, you're going to do 12 minus 6. So our final answer is 2.125 times 10. 12 minus 6 is 6. So that's your final answer. And now I encourage you to pause the video and try example 8 on your own. And assuming you have given this one a go, let's go through it. So we have 2.4 times 10 to the negative 17th power, all divided by 3.6 times 10 to the 5th power. So as before, let's divide. So 2.4 divided by 3.6, that becomes 0.66. When we round up, because this is repeating, we can round it up 2.7. And then we're going to need to use the exponent rule. So times 10, negative 17 minus 5 is negative 22. Now, technically, this is not your final answer. And that's because, recall, there's a rule for scientific notation where A can be equal to 1 but less than 10. So it has to be equal to 1 or less than 10. So what this means is that this is not our final answer. We need to move that decimal place to the right by 1. So our final answer is going to become 6.67 times 10. And because we moved it over to the right by 1 value, is our exponent going to become negative 21 or negative 23? It's going to become negative 23. That's your final answer. Looking at example number 9, we have 5.3 times 10 to the 8th times 3.1 times 10 to the 9th. So for this one, this multiplication is also fairly simple. All you have to do is know your exponent rules for when we multiply two things. So recall that x times a times x to the b equals x to the a plus b. So we just have to use that simple exponent rule that we've learned, or that we learned in 5.1. So all we have to do here is do 5.3 times 3.1. And then we're going to carry along that times 10 to the 8 plus 9 power. So this becomes 16.43 times 10 to the 17th power. Now, this is not our final answer because our a value here is greater than 10. So we just need to move this decimal place over by 1. So we get 1.643 times 10 to the 18th power. Alrighty, for example, number 10, I encourage you to pause the video and try this one on your own. And assuming you have given it a go, let's go through it. So we have 5.6 times 10 to the negative 5th, all multiplied by 3.6 times 10 to the negative 4th power. So to simplify this, we're going to do what we did in example 9. So we're going to do 5.6 times 3.6, which gets us 20.016 times 10. We're going to add our exponents, so negative 5 plus negative 4. Well, that becomes negative 5 minus 4. So we're going to have negative 9 as our exponent. Now, as we see in example 9, this is not our final answer. So we're going to need to move that decimal place to the left by 1 value. So our final answer is going to be 2.0. Oop, I apologize. Here, my value is incorrect. It was supposed to be 20.16. But we still have to move that decimal place over, so we're still going to get 2.016 times 10 to the negative 8th power. Alrighty. So for the last two examples of this section, we're going to be working with scientific notation and doing a couple word problems. So for example 11, we are given a data center uses 4.2 times 10 to the 7th power joules of energy each hour. How much energy does it use in 24 hours? So we know that per hour we use 4.2 times 10 to the 7th power of joules. So to find out what it uses in 24 hours, all we have to do is to multiply this by 24. So we get 4.2 times 24, and then we're going to carry along the times 10 to the 7th power. And 4.2 times 24 is 100.8. And then we're going to carry along that times 10 to the 7th power. Now, this isn't our final answer, recall, because a is larger than 10. So we're going to need to move that decimal place to the left 2 places, 1, 2. So we're going to get 1.008 times 10 to the 9th power. So our final answer is 1.008 times 10 to the 9th power. And we're going to need to label what our units are. So this is joules. And if you want, you can say per 24 hours. Alright, so for example 12, I encourage you to pause the video and try this one on your own. And assuming you have given it a go, let's go through this. So we have the word problem. The speed of light is 3 times 10 to the 8th meters per second. A certain spacecraft travels at the speed of 2.5 times 10 to the 3rd meters per second. So we want to know how many times faster is the speed of light compared to the spacecraft. So the one note I want to make here, because this word problem can be kind of confusing for some people. So the phrase how many times faster always means you're going to take the greater value of whatever you're trying to figure out. You're going to take that greater value and divide it by the smaller value. And that is because this tells you how many copies of the smaller speed fit into the larger speed. Okay. So now that I wrote that, so we know we're gonna divide these two numbers. Now I want to ask yourself, which number is larger, 3 times 10 to the 8th or 2.5 times 10 to the 3rd? Well, because 8 is larger than 3, 3 times 10 to the 8th is our larger number. And then we're going to divide that by 2.5 times 10 to the 3rd. Well, 3 divided by 2.5, that's 1.2. And we're going to do times 10. And then our exponents, we're going to subtract it. So we're going to do 8 minus 3. This becomes 1.2 times 10. 8 minus 3 is to the 5th. So this is your answer. And this means that light, if you were to convert this number to a rational number, this means that light is 120,000 times faster than the spacecraft.